So in the yesterday's class we proved that if you consider a sequence of functions and if each function fn is integrable and if fn converges to f uniformly, then f is also integrable and the sequence of numbers integral fn that will converge to integral of f. Okay. Let us also see the interpretation of these results in a language of this metric spaces. We have already seen that, for example, if you take this space CAB, that is space of all continuous function with this matrix d suffix infinity, we have seen that our earlier result about the uniform convergence and continuity, that implies that this is a complete metric space. Okay. And we have also observed quite early that convergence, uniform convergence is basically convergence in this metric. Okay. Alright. Now let us see how our yesterday's result of integration can be interpreted in this. Okay. Now we also know that this CAB is a vector space. Okay. So one can define a map phi from this CAB to R. Let us talk of Riemann integrals only for the time being. As follows, I define phi of f as integral a to b fx dx. Okay, all right. Then you already know that this is a linear functional. In fact, we have proved that if, for example, following the various theorems about the integration that we proved, phi of f1 plus f2 is phi f1 plus phi f2, phi of alpha times f will be alpha times. So phi is a linear functional. Okay, phi is, that is, of course, that is something that is already known. Okay, phi is a linear functional. Okay, and what did we prove yesterday? That if fn converges to f uniformly, okay, fn converges to f uniformly, then integral of fn converges to integral of f. Okay, in other words, if fn converges to f in this d infinity, that is d infinity fn f tends to 0, this implies phi of fn tends to phi of f, right? Remember, phi fn and phi f, they are numbers. Okay, phi fn and phi fn. Okay, so that means if fn converges to f in this metric, then phi fn converges to phi f. Okay, now what is the meaning of this? It means that phi from this CAB to R is a continuous function. Okay, right? That is one of the ways of describing continuity is that whenever xn converges to x, f of xn converges to f of x, that is equivalent to saying that f is continuous. So that is what we have said here. Whenever fn converges to f in this metric, phi fn converges to phi f. That is same as saying that phi is a continuous function. Since it is already a linear functional, it means that phi is a continuous linear functional. Okay, all right. Then there is one more thing here. While describing the results about the integrals, we had taken this upper limit as b. Okay, but that is not very much essential. Okay, one can let this upper limit vary also. For example, I can consider integral a to x fnt dt. Okay, suppose I can consider integral a to x fnt dt. Okay, and then this will converge to integral a to x ft dt. If fn converges to f uniformly, whatever x you take in AB, then integral a to x fnt dt will converge to integral a to x ft dt. So it means that this upper limit need not be b. Okay, it can be any number. Now whatever you say about the upper limit, one can say the same thing about the lower limit also. Okay, instead of a you can take some other number. So consider integral from y to x fnt dt, where y and x are any numbers lying in AB, that will converge to integral y to x ft dt. Okay, so there is nothing very particular about this numbers a and b. That in other words, if you take any subinterval of the AB, then integral of fn over that subinterval will converge to integral of f over that same subinterval. Okay, all right. That's about the integration. Now let us go to the discussion of uniform convergence and differentiation. And differentiation. And one can ask an analogous question here. Okay, suppose we have a sequence fn, uh, uh, fn from AB to R, and suppose fn converges to f uniformly, fn converges to f uniformly, then suppose each fn is differentiable. Okay, suppose each fn is differentiable. Okay. Then what we might expect, that if each fn is differentiable, then we might expect that f also is differentiable, and not only that, we should also expect that fn prime converges to f prime. Okay, right. We have already seen that this is false as far as pointwise convergence is concerned. Okay, right. But what is also true is that this is the question is, suppose each fn is differentiable, the question is this. Okay, is f differentiable? Is f differentiable, and does fn prime converge to f prime in whatever sense, pointwise, uniformly, whatever. Okay, okay, and answer to both the questions are no. Okay, that even if fn converges to f uniformly, okay, it is not necessary that f must be differentiable, and even when f is differentiable, this may or may not happen. Okay, and it is fairly easy to construct examples. In fact, subsequently we will prove a very powerful theorem. uh, Perhaps you may have already heard of that theorem. It is called Weierstrass theorem. Okay, Weierstrass theorem says that given any continuous function, you can find a sequence of polynomials which converges to that continuous function uniformly. Okay, so you can obviously find a function which is continuous but not differentiable. Okay, and to such a function also you can find a sequence of polynomials. Now every polynomial is differentiable. Okay, but the limit will not be differentiable. Okay, also it can happen that fn converges uniformly, but fn prime need not be convergent at all. Okay, fn prime need not be convergent at all. Okay, that is fairly easy to show. Suppose we take this example. Okay, fn x is, let us say, sin nx by root n, sin nx by root n. Then is it obvious that this tends to 0 uniformly, whatever interval you take, forever. Okay, this tends to 0 uniformly. Okay, you can take m suffix n will be less than or equal to 1 by root n. Okay, in fact m suffix n will be, and that mn tends to 0. Okay, so that is easy to show. Okay? But what about fn prime x? That will be n cos nx divided by root n, right? So that will be root n cos nx, root n cos nx. Okay, and you can see that this becomes unbounded. Even if you take x equal to 0, this sequence will be simply root n. So this is not a convergent sequence at all. Okay, so as far as the derivatives are concerned, the things are somewhat bad. Okay, that is, even with uniform convergence you cannot assure various things. Okay, so for the derivatives what we have to do is that we have to assume something more. Okay, namely that not only that fn converges to f uniformly, we have to also assume that fn prime converges uniformly. Once you assume that fn prime converges uniformly, that is a fairly strong assumption. Okay, then you don't need even this. Okay, we can in fact simply assume that fn converges to f pointwise, or even at one particular point also, that will be sufficient. Okay, so let us just see what does the theorem say. Okay, the theorem is the following. Okay, suppose fn are functions from AB to R. Each fn is differentiable. Fn is differentiable in AB. and as far as the convergence is concerned, we will say the two things. For some x naught, fn x naught converges to f x naught, let us say, okay, that is fn x naught converges to f x naught for some x naught in AB, and fn prime converges to G uniformly. Okay, so fn from AB to R, we have to take these two functions also, fn, f and g, all these are functions from AB to R. Okay. F and g. So what are the assumptions? Each fn is differentiable. If at some point fn at x naught converges to f at x naught, then fn prime converges to G uniformly. Okay. Fn prime converges to G uniformly. Then what is the conclusion? Conclusion is that if that is the case, f is differentiable and its derivative is same as G. Okay. Then these are all the hypotheses. Then f is differentiable okay, f is differentiable, and okay, in fact even before that I would say that since that is not we are assumed, okay, fn, then fn converges to f uniformly, fn converges to f uniformly, f is differentiable and f prime is equal to G. Actually, if we make one more stronger assumption, suppose we also assume that fn prime is also continuous for each n, then the proof becomes very easy. Then all that we can do is that we can use this previous theorem. Okay, we can, since fn x naught converges to f x naught, for any x you integrate from x naught to x. Okay, so consider integral x naught to x fn prime t g dt, that goes to gt dt, and then show that because of the earlier theorem, integral of x naught, because we have seen that upper limit and lower limit can be anything. So I can take integral x naught to x, instead of fn I will take fn prime. Then by this theorem it will mean that integral of fn prime t dt will converge to integral gt dt, and then it is easy to show that that is same as an integral of fn prime between x naught to x will be nothing but fn of x minus fn of x naught. Okay, and we already know that fn of x naught converges to f of x naught. So using that it will be fairly easy to show that f is differentiable and its derivative is same as G. Okay, but if we don't assume that fn prime is continuous, then the proof is slightly involved. Involved in the sense we will need some more work to do. Okay, and that is what we shall do. Okay. Again, the idea is that, okay, let us take the things one by one. First thing is we want that fn converges to f uniformly. Okay, fn converges to f uniformly. Then we have seen that one of the ways to show that a sequence of function converges uniformly is that you show that it satisfies Cauchy criteria. Okay, you show that it satisfies Cauchy criteria. Okay. Then what do we know about fn? We only know that fn at x naught it converges. At other points we don't know. Okay. To show that it satisfies Cauchy criteria, what we'll have to show is that okay, that is if you look at fnx minus fmx, okay, we have to show that this quantity can be made arbitrarily small by choosing n and m sufficiently large. Okay, and that small number should be independent of x. Okay, in other words, what I should show is that, let us say that mod fnx minus fmx is less than or equal to some alpha n. Okay, for every x in AB, and then that alpha n goes to 0. Okay, all right. But what we know is that fn x naught converges to f x naught. Okay, so if I take fn x naught minus fm x naught, that is going to be small. Okay, so So our idea is basically we add and subtract, okay, and similarly what we know is that Fn prime converges to G uniformly. So this Fn prime satisfies the Cauchy criteria, okay. So there instead of Fnx minus Fmx, if I had taken Fn prime x minus Fm prime x, okay, that is easy to make, that quantity can be made arbitrarily small, but basically we use all these facts, okay. So what is the idea? We'll take this minus this Fn at x naught minus Fm at x naught, okay. Suppose we are able to show that this can be made arbitrarily small, okay, and independent of x, okay, then is it clear that then it will mean that this is also small, because I am only adding a small quantity here, okay, I am adding a small, okay. But what can we say about this? This is the thing, but if you look at the function, suppose we look at the function Fn minus Fm, okay, if you look at the function Fn minus Fm, it is a difference between the values of this function at x and x naught, okay, it is a difference between, right, okay, and moreover this is a differentiable function, okay. So one can use mean value theorem, okay, one can use mean value theorem and say that this will be the thing, but x minus x naught into the derivative of this at some point like between x and x naught, okay. Okay, so we can say that this is same as by mean value theorem, we can say that by Lagrange's mean value theorem, this is same as x minus x naught into Fn minus Fm derivative of this at some point xi, let us say, okay. So which is same as saying that Fn prime xi minus Fm prime xi for some xi in, okay, xi between x and x naught, let me say, because I don't know which is bigger and which is smaller, okay, between x and x naught, okay. Now the idea is this, we know that this quantity Fn prime xi minus Fm prime xi, that can be made arbitrarily small, and that will be arbitrarily small independent of this xi, whatever is this xi, because we know that Fn prime converges uniformly, okay, Fn prime converges uniformly. So this satisfies Cauchy criteria. So let us start from this, okay, that is the starting point of the proof, okay. So we can say that okay, let me write it here, okay, proof. Okay, so let us say that let epsilon be bigger than 0, okay, since Fn prime converges uniformly, since Fn prime converges uniformly, okay, you can say there exists n0 in n such that m and n bigger than or equal to n0, m and n bigger than or equal to n0, this implies mod Fn prime, let me call it y, Fn prime y minus Fm prime y, this can be made less than or equal to any arbitrary number for every y in AB, okay. I will take that number as, because here we have to add and subtract this quantity, so I will make that less than epsilon by 2, but here the multiplication is there also by x minus x naught, so this will remain bounded by b minus a, okay. So we will say that this is, we shall choose n0 such that whenever m and n are bigger than or equal to n0, this is less than epsilon by 2 times b minus a, okay, okay. All right, okay. Now consider some such m, now consider some m and n which are bigger than or equal to this n0, okay. Consider m and n bigger than or equal to this n0, okay. Let me take it here, okay. Consider m and n bigger than or equal to n0. Then for those m and n we have done all these calculations. Of course this is true for any m and n, but now we will apply for those m and n bigger than or equal to n0. I will take absolute value everywhere, okay. So okay. Now this mod x minus x naught, x and x naught both are points in the interval AB, okay. So mod x minus x naught is less than or equal to b minus a, okay. Mod x minus x naught is less than or equal to b. So this is less than or equal to b minus a, and this is less than epsilon by 2 into b minus a. So which is so the whole thing is less than, okay, in fact this is strictly less than, so I can take it strictly less than epsilon by 2, okay. Alright, okay. What next? Next we can say that since fn x naught converges to f x naught, I can again do the same thing. I can find some, let us say n0 prime, okay, such that okay, here itself let me call it n0 prime. So this will be, let us say n0 double prime, such that okay, this, I think these primes are unnecessarily complicating. Let us call it n1, okay. Let us call it n1. So consider this m and n bigger than or equal to n1, okay. Then what I would say is that there will exist n2 such that whenever m and n are bigger than n2, fn x naught minus fn x naught is less than epsilon by 2, okay. So what is the argument? Since fn x naught, see the argument is fn x naught is a convergent sequence, hence it is a Cauchy sequence, okay. Since fn x naught is a Cauchy sequence, there exists n2 in n such that m and n bigger than or equal to n2, this implies mod of fn x naught minus fm x naught is less than epsilon by 2, okay. What is to be done after this is clear, okay. You take n0 as the maximum of n1 and n2, okay. Let n0 as maximum of n1 and n2, then for m and n which is bigger than or equal to this n0, both of these inequalities are satisfied, okay. Let us continue here. So what we say is for m and n bigger than or equal to n0, consider now and x in AB, consider mod fnx minus fmx, okay, alright, and all that you do is add and subtract fnx naught minus fmx naught, okay, add and subtract. So this is less than or equal to mod fnx minus fmx minus fn at x naught minus fm at x naught and plus mod fn at x naught minus fm at x naught. Each of this is less than epsilon by 2, okay. This is less than epsilon by 2 because of these considerations here. Remember the first quantity is less than epsilon by 2 because of the second assumption, fn prime converges to G uniformly, and the second is less than epsilon by 2 because of that first assumption that fn x naught is converges to f of x naught, okay. So this is less than epsilon by 2 plus epsilon by 2, which is epsilon, okay. So what did we show? That given any epsilon, there exists n0 such that whenever m and n is bigger than or equal to n0, mod fnx minus fmx is less than epsilon for every x in AB, okay, which is same as saying that fn is uniformly Cauchy, okay. So this implies that fn is uniformly Cauchy, or fn satisfies Cauchy criteria. Cauchy criteria and hence converges uniformly, uniformly to, let us say, some f, okay, converges uniformly to some, that is whatever the function it converges, that function we shall call f, okay, that function we shall call f. So now what remains is to show that this f is differentiable and its derivative is same as that function g. What is the function g? It is the function to which this fn prime converges uniformly, okay, that is what is remaining to be shown, okay, alright. Now to show that, let us proceed as follows. So let us take some x in AB. Let us take some x in AB, and we shall consider a function for let us say for t in AB, for t in AB and t not equal to x. Okay, for t in AB and t not equal to x, define okay, several functions. First function I will define is phi of t. Phi of t, that I will define as follows: ft minus fx divided by t minus x. Okay, ft minus fx divided by t minus x. Okay, and I will define phi n of t as fn t minus fn x divided by t minus x. Okay, you can understand why these functions are defined, okay, because we are interested in the differentiability. So to show that, we want to show that f is differentiable, okay, we want to show that f is differentiable, that is same as showing that the limit of phi t as t tends to x exists, okay, limit of phi t as t tends to x exists, okay. But what about phi n t? In case of phi n t, we know that limit of phi n t as t tends to x exists, that is same as saying that fn is differentiable. That is something we have assumed, okay. So this limit is exists, and that is something that we know already, okay. So let me just say that now the idea is as follows, okay. Suppose we show that phi n converges to phi uniformly in this interval AB except at t not equal to x, okay, okay. Then of course then this x is a limit point of this AB minus x, right? Remember our theorem about the limit, okay. Let me first say what we are trying to do. We'll claim this, okay. Okay, you can, I will say that phi n t converges to phi t uniformly not on the whole interval AB, but in the interval AB minus x, okay, in uniformly on the interval AB minus this set singleton x, okay. Let me remind our theorem about the limit, okay. We had said that if fn converges to f uniformly on E and if x is a limit point, okay, then limit of fn as t tends to x goes to limit of fx as t tends to x. So suppose this is proved, okay, suppose this claim is proved, then one can say that limit of phi t as t tends to x, okay, and see limit of phi n t as t tends to x is nothing but fn prime at x. Is that clear? That is limit of phi n t as t tends to x is nothing but fn prime x, okay. Let me remind you that theorem once again in case you have forgotten. The theorem was the following: fn, even before proving the theorem about the quadratic, we had taken the functions fn from E to R, and Tx was a limit point of E, okay, and we had said that limit of fn t as t tends to x, we had taken these numbers as some ln, okay, okay, we have taken this number as some ln, and what was the assumption? That fn converges to f uniformly if Fn converges to F uniformly, then what we had said was that limit of this ln as n tends to infinity exists, also that is that limit is same, limit of this ln as n tends to infinity exists, and limit of this ft as t tends to x exists, and that limit is same as this limit. Okay, this was our in fact one of the first theorem about uniform convergence. This is same as limit of ft as t tends to x. Okay. Okay. We are going to use that theorem for the functions phi n and phi. Okay. Suppose we show that phi n t converges to phi t uniformly, and limit of phi n t as t tends to x exists, that is same as Fn prime x. So if this claim is proved, if this, let us say, if this claim is proved, or if this claim is true, if this claim is true, then what must happen is that then limit of phi t as t tends to x, this limit should exist. Okay, this limit should exist, and that should be same as limit of this Fn prime x as n tends to infinity. Okay, limit of Fn prime x as n tends to infinity. Remember, this Fn prime x is something like this ln. Fn prime x is takes the place of this ln. Okay, that is limit of Fn t as t tends to, limit of phi n t as t tends to x is Fn prime x. Okay. Okay. But we have already assumed that Fn prime converges to G. So this right hand side is nothing but G prime x. Okay. Right hand side is nothing but G prime x. Okay. Sorry, G of x. I am sorry, you are right. It is nothing but G of x. Okay. And so what it says is that this limit exists, and that limit is same as G of x, which is same as saying that f is differentiable. Saying that this limit exists is same as saying that f is differentiable, and that limit is same as G of x is saying this, that f prime x is equal to Gx. That is f prime x is equal to G of x. Okay. Okay. So what remains now? What remains is to prove this claim. Okay, we assume that if this claim is proved, then whatever we wanted would be proved. Okay, once this claim is true, once the claim is proved, the proof of the theorem is over. Okay, all right. Now what is involved here? We want to show that phi n converges. See, remember, phi n t converges to phi t pointwise. There is no problem about that. Okay, about that there is no problem. Okay, because we already shown that Fn converges to F uniformly. So Fn t will converge to Ft, Fn x converges to Fx. Okay, so only really thing to show is that phi n uniform convergence, and we shall use the same technique as we had done earlier. Okay, that is, we shall show that phi n is satisfies Cauchy criteria. Okay, phi n satisfies Cauchy criteria. So if we consider, let us say, phi nx minus phi mx. Okay, phi nx minus phi mx, then that is same as Fnx minus Fnt, then minus Fmx minus Fmt, this divided by t minus x. Okay, and we shall use the same thing or same technique which we have used earlier, namely mean value theorem. Okay, because if you look at this Fnx minus Fnt and Fmx minus Fmt, these are nothing but the values of the function Fn minus Fm at x and t. Okay, if you look at again the function Fn minus Fm, you have Fnx minus Fmx and then minus Fnt minus Fmt, right? So what we can say is that by mean value theorem, we can say that by mean value theorem there exists xi between between x and t such that fnx minus fmt then minus fnx minus fnt minus fmx minus fnt, that is nothing but t minus x into fn prime at xi minus fm prime at xi. Okay, is it okay? We are applying mean value theorem to this function fn minus fm. Okay, remember here we have fn minus this whole thing can be written as this numerator is nothing but fn minus fm at x minus fn minus fm at t. Okay, 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 what you are saying is this will be x minus t. Okay, fine, this will be x minus t, fine. It will not matter because we are going to take absolute values. Okay, all right. Okay. So finally what will get is this t minus x will cancel with that x minus t with a negative sign. So since we are going to take absolute value, what we will get is this. Okay, mod phi nx minus phi m, mod phi nt minus phi mt. This will be equal to mod fm prime xi minus fn prime xi for some xi lying between t and x. Okay, do you agree? After applying mean value theorem and after cancelling this t minus x and x minus t, etc. Okay, okay. Now what is to be done after this is clear. Okay, we already know that fn prime converges to g uniformly. Okay, we already know that fn prime converges to g uniformly. So we can always find, given epsilon, we can always find some. Okay, let me just write. Okay, since fn prime converges uniformly, there exists n0 in n such that m and n bigger than or equal to n0. This implies mod fn prime xi minus fm prime xi is less than epsilon for all xi in AB. That is important, for all xi in AB. Okay, right. So going back here, since this is less than epsilon, it will mean that this is also less than epsilon for, since this happens for every xi, this is less than epsilon for every t in AB. For every t in AB. Okay, it's basically application of mean value theorem once again. Okay, okay. And so this shows that this sequence phi n is uniformly Cauchy. The sequence phi n is uniformly Cauchy, and hence it follows again that phi n converges to phi uniformly. We already know that phi n converges to phi pointwise. Now we know that phi n converges uniformly, so the limit function must be same as phi. And as we already observed, once this claim is proved, the proof of the theorem is over. Okay, okay, okay. So this says about the relationship between uniform convergence and the differentiation. And as in the earlier case, we can also ask similar questions about the series. Okay, that is, till now we have taken fn converges to f. Suppose we look at the series like this: sigma fn converges to f, sigma n going from 1 to infinity. Suppose here the convergence is uniform. Okay, but then also you cannot say immediately that you can differentiate the series term by term. It does not follow that sigma fn converges to, sigma fn prime converges to f prime. We will need additional condition, namely that sigma fn prime should also converge uniformly, and this original series should converge at least at one point. then we can differentiate the series term by term. So let us just record those observations. So corollary is this, okay. If sigma fn prime converges to f uniformly, okay, let us say not f now, let us call this g uniformly, and sigma fn is equal to f point wise, let us say. Actually it is enough to say at least at one point by using that theorem, then f is differentiable and its derivative is nothing but g, okay, and f prime is equal to g, okay. In other words, sigma fn prime is equal to, if sigma fn is equal to f, sigma fn prime is equal to f prime, which basically means that you can interchange the operations of summation and differentiation. That you can do provided this happens, sigma fn prime equal to g, that is the series obtained by differentiating each term must be uniformly convergent, okay. Then only you can interchange the summation and differentiation, okay. Okay. Now let us see how all these theorems which we had consider about the uniform convergence and various things, uniform convergence and continuity, uniform convergence and integration and differentiation can be used, okay. There are several uses of this. There are two major things that are coming into picture. Those are certain kinds of series, and in proving that those series are uniformly convergent, they give continuous functions, give differential functions, etc. One set is what is called power series, something that you have heard of already, okay, power series, okay, and other types of series are what are called Fourier series, okay. Now these are also something like power series, but here the functions involved are polynomials, and here the functions involved are what are called trigonometric polynomials, okay. So these are some of the positive results that will follow from the discussion of uniform convergence, okay. There is also one very interesting result which in some sense is negative, but it is interesting in the sense that it says something different from our usual intuition says, okay. And that is the following, okay, that is, if you look at if you say that something is a continuous function, you are expected to think that its graph will be something like a curve, okay. Now if you have that kind of idea, then it will appear that whenever the function is continuous, it has to be differentiable also, but you already know that that is not true. The graph can be something like this, okay. So function can be continuous but not differentiable, okay. This is a well known example of modulus. Suppose you want a function which is continuous but not differentiable at 2 points, okay, one can have a function like this, okay, or suppose more than 2 points, it can be a function something like this, okay. That is, so it is fairly easy to construct a function which is continuous everywhere, let us say, but not differentiable at 2 points, 3 points, etc., okay. But suppose one asks a question, does there exist a function which is continuous everywhere but not differentiable anywhere, okay. That is, does there exist, is the question clear? Does there exist a function which is continuous for all x in R but not differentiable for any x in R, okay. Then you will see that our usual intuition does not help us in answering that question, and one feels that such a function may not exist at all, okay. But the answer is yes, there is a function, there does exist a function which is continuous everywhere but not differentiable at any point, okay. And the construction of such function requires everything that we have done so far about the uniform convergence, continuity, differentiability, etc., okay. So let us just make some preparation. By the way, it is not very difficult, constructing that function is not very difficult. What it involves is little bit of calculations and some use of all these theorems which we have made, okay. Now to begin with, let me first make a few observations. One observation which I have already made, let me repeat it once again. You know that saying that some limit of fx as x tends to a, suppose this is equal to L, okay. We have already seen that this is equivalent to saying that if you take any sequence xn converging to a, then f of xn must converge to L, okay. If you take any sequence xn converging to a, f of xn must converge to L, okay. Suppose I apply this concept to derivatives, okay. Suppose I apply this concept to derivatives. Suppose f is differentiable at x. What is the meaning of that? It means that limit of, let us say again use, let us say limit of ft minus fx at t minus x, limit as t tends to x exists. Suppose f is differentiable, then this is same as, this limit is same as f prime x, okay. This limit is same as f prime x, okay. What is the, how do I convert this using this earlier idea? This will mean that if I take any sequence, suppose I call it sequence alpha n, suppose I take any sequence alpha n converging to x, okay, then f of alpha n minus fx divided by alpha n minus x, limit of that as n tends to infinity, that should be same as f prime x, okay. That means let us suppose, if that means this is so, this is equivalent to saying that for every sequence alpha n converging to x, limit of f at alpha n minus fx divided by alpha n minus x, limit of this as n tends to infinity, this limit should exist and that limit should be same as f prime x, okay. Now this is fairly easy, okay, that follows immediately by applying this principle, okay. But what we want is not this, a slight modification of this, okay. What I want is that suppose instead of one sequence alpha n, suppose you take two sequences alpha n and beta n, and suppose both of them are converging to x, okay, and I look at these ratios, f at beta n minus f at alpha n divided by beta n minus alpha n, and take the limit of that as n tends to infinity, where what are beta n and alpha n? Beta n and alpha n are two sequences converging to x, okay, beta n and alpha n are two sequences converging to x. Now the question is whether the limit of such thing is also same as f prime x, that is the question, okay. Okay, and the answer is in general this is not true, okay. If you take alpha n and beta n as totally arbitrary sequences converging to x, this may or may not happen, okay. But if you choose alpha n and beta n in a particular way, this is true, okay. And what is that particular way? Let me just state that now, okay. Let us say this, okay. For theorem, let us say that let f, suppose f is defined on some interval ab, open interval, because we are talking about differentiability, we will take open interval, f from ab to r is differentiable at, let us say, sub x in ab, and we take two sequences alpha n and beta n in the following manner, okay. Let a less than or equal to alpha n less than or equal to x less than or equal to beta n and less than or equal to b, that is all alpha n's are less than or equal to x and all beta n's are bigger than or equal to x, okay, for all n, and both of them converge to x, okay, and limit of alpha n as n tends to infinity, this is x, and limit of beta n as n tends to infinity is also x. Then this is true, okay. Then limit as n tends to infinity of f of beta n minus f at alpha n divided by beta n minus alpha n, this is equal to f prime x. Okay. Okay. And we shall first prove this, and then we shall use this to construct that function which is continuous everywhere but differentiable nowhere. In fact, that was a very famous function first constructed by Weierstrass, again, who is famous for several things. Okay. Okay. And this function construction of this, because this said something totally opposite to whatever is the usual intuition of everybody, and that led to deeper thinking about how a function is to be defined, etc. Because till that time everybody used to think that function means something defined by a formula. Okay, functions mean something like 2x cube plus 3x square, or fx is equal to sin x, or functions mean something defined by that kind of formula. But after this example came, everybody thought that the concept of function has to be looked at more carefully, and then we have the modern definition of functions after several people contributed to that definition. I mean, we shall not go into that kind of history, but we shall look at the construction of this function in tomorrow's class, because today the time is already over.